Uh,
All
Hello
right.
everyone. I'm
Okay, I
Amin.
mean, I will do the intro and I will leave you with the
Okay.
talk. Yeah, because I didn't notice the message. So welcome everyone in our second day of our big little festival of developers. This is our 10th anniversary of the festival actually, and we are happy to have you here with us, everyone. So today, in this talk series, in this first session of the talk series, we'll be joined by Mr. Amine KERKENI. He is a software engineer, a Google developer expert in machine learning from Tunisia, and director of engineering at InstaDeep, the Tunisian company which we all know for building advanced decision-making systems for the enterprise. So welcome abroad, Amine, and thank you for being with us today.
Thank you for the invitation. I'm very glad to be speaker in this event for Algerian audience, and I hope you'll enjoy my talk today. So today I'll be talking about how to do reinforcement learning in practice and tackling the problem not from a research point of view or like explaining the basics, maybe, even though I'll explain some technical details about reinforcement learning, but I'll focus more on what makes a project like this succeed, what are the problems you may encounter, how to organize your team if you work on such projects, and what makes it different from machine learning, like classic machine learning project and even classic software. So I'll start by talking a bit about history of software development. So I think we're almost 70 years from the invention of the term software. And in the beginning, it was like the first persons who coined the term were thought like it was a prank or something, because in the 50s everything was hardware. If you want to do automation, you have to do everything in using electronics and hardware, and gradually software ate everything basically. And this generated a lot of challenges for such projects. And from early on, people thought about how do we organize teams and projects like this? Do we use things coming from civil engineering? Is it different? And so on. And the first probably attempts were in this between the 50s and 70s. Like it was not something coming from out of nowhere. Like during 20 years, people tried to refine what we call the waterfall model, which is a super sequential workflow to organize the life cycle of software development. And we will see it in detail a bit later. Then we, like most people, found that it's super difficult to work with this super rigid way of organization, and tried to introduce a kind of iterative process to the life cycle. And we've seen in the end of the 80s the appearance of spiral models, what we call so it's basically the waterfall model, but where we inject some kind of iteration. And then the 90s and years 2000, like the dominance of agile methods, Scrum, which are more iterative approach, where we take into account like the real constraints of a software project where everything changes and like working in super unstable uh, environment. And the last 10 years, we see the like the appearance and dominance of approaches like DevOps, basically deploying and fixing the product at the same time. So there's no like no separation between deployment and development. And maybe you all have heard about DevOps role in companies, which is kind of the role that appeared with the methodology. And it's related to the fact that software migrated from being something you install on your laptop or your desktop machine to web-based platforms that run all the time. So you don't really have binary distribution. So we maintain software that run in the cloud and so on, which make it super difficult to update the tool, answer like changing requirement from users, uh, and so. And we can like see basically the waterfall model as what you see in the on the left, where we start from specification. We talk to the customer, we collect a requirement, write that on paper, make him sign with his blood, and then we start the design and we never look back again. Then once we design the architecture, we start executing it and coding basically. And once we finished coding, we start testing. We ship the product, and then we switch to maintenance mode. And you can see here, we never look back. Like once we finish a phase, we consider that we finished our job and we can't touch anything from the past phases, which creates a lot of problem. The first one is contractual, like basically the customer changes his mind after a few weeks, months, and then they fight on the contracts. Did I say this? Did I say that? So it made project super conflictual, and thus people thought about new approaches where we introduce the possibility of iteration. So we don't go for long periods with no communications with the client, but we, from the beginning, we try to make a plan where we have very short sprints, usually 3 weeks to a month maximum. And at the end of each sprint, we try to create a working software that the client can use, at least in a prototype way, and give feedback. And based on this feedback, we adjust everything. So you can see the 5 phases we've seen before injected inside the iteration loop of the agile methods in general. But do these approaches apply to machine learning? The reality, it's complicated. First, like 85% of ML project fails. It's like we used to see this in software in the 90s, early 2000, this kind of failure number. Now you take a regular, like a normal software project, usually you have probably 10-20% risk of failure. We don't have this kind of risks anymore. But you see, in machine learning, it's quite different, and it's related to a lot of reasons. The first one, ML teams are quite different from software teams because it's difficult to get the people that master all the parts of a machine learning based system. So you have to create teams where you have software developers, Devops, sometimes front-end developers, statisticians or mathematicians, or what we call now machine learners. And people from different background, and making such team work together is a challenge in itself. Second, the projects are like have a high ratio of uncertainty. You like usually you start the project and you don't know exactly what to expect from the model. Like when you start a software project, okay, you have to automate one task, you know at the end that you will do that task. But in machine learning project, when you start, you have data that you don't, like you sign the contract, you have the data that you do know nothing about yet. You have to study it. So you don't know what to expect. Are we capable to take decision from that data or not? This is big question that you can't answer before planning the project. So it makes the project super hard compared to software. The third problem is also the customer itself and the managers, if it's an internal project for a company. And usually managers or business people do not understand machine learning. Like they think it's like software. Okay, I give my requirement and just get things done. But here we are driven by data most of the time. And the data is generated by the internal processes of the company. It may change due to a lot of reasons. It can be the customer behavior, change in regulation, change in the external environment of the company. So it's quite difficult to define KPIs before starting a project. Doesn't mean we don't have to do it, but it's super challenging compared to classic software project. And maybe the fourth problem is the speed of disruption that you see in the field right now, at least for the last few years. And the trend will keep happening for at least a decade. So every 6 months, one year, every year, you see a new revolution in deep learning and machine learning. A recent example is how transformers are changing deep learning in general. For a long time, we thought like transfer learning is only possible in applied machine learning when in problems that are related to vision. But 3-4 years ago, we started to see that we can do transfer learning for NLP, for example. It's where transformer appeared first. So we start to see people using these attention-based and transfer model and transformers, like in processing language, and then other fields of AI started thinking why we don't use it in other tasks that we see in the regular business problems. So it's kind of taking over everything right now, and I'm sure like in 6 months or a year we'll see a new thing, a new revolution with the same kind of impact on the way we drive machine learning projects. So given all these challenges, people started also thinking about new ways how to organize machine learning projects. Maybe the more mature one is called CRISPR DM, which is kind of life cycle inspired from what we've seen before, agile and things like that. But initially dedicated to data mining, so the DM is for data mining, but it fits exactly what we need to do for machine learning. So basically, we start with analyzing business understanding. Uh, Once we understand how the business operate, what problems are we trying to solve, we try to collect data. If the company has data, we try to have kind of initial analysis of that data. If they don't have, we put in place processes to collect data, and we iterate. Maybe we can refine the needs based on what we find in this data analysis phase. Once we understand what's in our data, we go to the next part, which is data preparation. Usually, if you want to use your data for machine learning, you'll have to clean it. You have to transform it in a way that the machine learning model can use it, and then you start the modeling phase. During the modeling phase, you may find some limits in the data and so on, so you have to iterate. Once you have a good model, you go to evaluation, and based on the new data you collect, you may have come back to the business partners and discuss again what to improve. So it's kind of iterative way. And as I said, like machine learning is kind of revolution in software. It has been happening for almost 10 years now. And I think the term was coined first by Andrei Karpathy, who's leading the AI team at Tesla. Yeah, maybe the fans of Tesla know about him. He's quite famous. And he coined the term software 2.0. Basically, for him, the new software is machine learning. So it will change the way we design technology stack. And you see it, for example, in Tesla, everything. The self-driving car is mostly based on capability, mostly based on deep learning and reinforcement learning. But the the classic part of software is going nowhere, because if you want to run a machine learning model, you will also need classic software for a lot of reasons, for the deployment, for the distribution, accelerating the learning, for analyzing the data, feeding it to the model, evaluation, interacting with the end user. So basically, you still have to do the classic software, but in addition, you also have to do what they call software 2.0. But as I told you in the beginning of the talk, I'm here to talk about reinforcement learning. So why am I talking about all this? It's because reinforcement learning is at the crossroad between classic software and machine learning. So, and for those who don't know what is reinforcement learning, is like a way to make machine learn tasks by experimenting. In machine learning and deep learning, we just take data, we label it. It may be a super expensive task to label data by humans. And then once we have this labeled data, we put a model to learn how to solve problems similar to the data that we collected. In reinforcement learning, as we will see later, it's a bit different. The agent or the system will learn by experience, like we human do. And what is noticeable is that the MIT Technology Review, which is a well-known press magazine, predicted in 2013 that deep learning was like a massive breakthrough. And again, in 2017, it predicted the same for reinforcement learning. So if we follow the same trend, reinforcement learning will be in a few years the equivalent of what deep learning is today. And usually, like if you look at the prediction of the MIT Technology Review in the last 3 decades, they almost always get it right. So they get this ranking every year by identifying disrupting technologies. So in general, they're quite good at predicting what will happen in the future. So what is reinforcement learning? Basically, when you have a classic program, you will, like the developer will take the task at hand, and he will instruct the machine what to do at each step. And like the programmer need to identify the way of solving the problem. Machine learning, like you look what happens in the past and tell the machine try to guess what will happen in the future, basically. Reinforcement learning, once it learned how to do the stuff, it will tell you what to do, basically. In here, so it's a bit kind of joke. So reinforcement learning will just tell you run. And how it works. So we have our agent, which is the what will, like the piece of the program or the algorithm that will take decision. This piece of program has the potential to act on an environment. The environment can be a real life environment. If you are driving, like if the agent is driving a car, for example, the environment is basically the car itself and what you observe from the outside world, traffic, etc. It could be, in this case, for example, push the brakes, turn left, turn right, push the throttle, and so on, stop, etc. And what it gets from the environment is what we call observation. Basically, in the case of self-driving car, it's the cameras getting the cameras that are onboarded in the car, and that will give observation of the outside world to our agent. And the reward can be like reaching your target, for example, going from work to home. Once you get to your target, you'll get a reward, and through this reward, the agent will learn. So initially, the agent will be super dumb. Usually, we initialize the agent with random weights, basically. And over time, with a change, like if we hit the target maybe once in 1,000 trial, we will start to see that okay, maybe the strategy that the agent took that in the episode that gave us a good reward is good, and I'll try to follow, like the agent will try to follow that strategy. And to the contrary to what seems, reinforcement learning is not that new. Like the approach itself was invented in the 80s, and it was called just reinforcement learning. Most of it worked on what we call tabular problems. So basically, your problem is a grid, and we try to learn how to reach your target. But what happens after deep learning came is we plugged neural networks to the approach. So before it was just a research thing that had no real practical application. But when we plugged neural networks to it, it started to deliver and at least try to. We are trying to solve real life problems with it. And the first breakthrough using this was uh, the famous agent developed by DeepMind, which led to its acquisition by Google, where they were the first to use the approach to to train superhuman agent that can play at Atari games, basically Space Invaders and Breakout and these kind of games. And so this was in 2014. And maybe the shock for the like the community was when DeepMind again have beaten the world champion in of Go, which is like Chinese, like chess. Um, uh, uh, and people were expecting this to happen in 30 years or something like that, because the combinatorial explosion of that game is super it's incredible. It's harder than chess, so you can't use brute force like was used by IBM in 97 for chess. And they basically taught this agent in 4 hours how to beat any world-class player in that game. So what's different in reinforcement learning compared to machine learning? The main problem uh, will be the need of simulator. So if you, for example, have a robot and you want to train an agent to move that robot, especially in complicated situation, you will risk to break the robot. As I explained, the agent will learn by doing random stuff initially. So probably if you deploy the agent to try to learn directly, first you will break the robot itself, and second, it will be super slow to learn, because you will probably have just one robot and you will try to move it. Each episode will take few minutes, but you need millions of actions to start learning. So for most cases, you need to build a simulator for your problem, and it can be more or less complicated depending on the problem. For example, Unity 3D provides what they call ML agent. It's like a framework that helps you build uh, simulations, game simulation that you could use in reinforcement learning, and a lot of people use that, for example, to train their agents. The second challenge for applying RL is that you need a sequential problem. So if I'd say I have a problem where I have to predict if an image is a cat or a dog, it's useless to use RL, because I just take one decision, and if you don't have a sequence of this decision and a delayed reward, basically I take an action now, but I'll see the impact after 3-4 actions. Like in chess, for example, think about chess. You move one piece in your chess table, and like probably this will be a kind of trap in 3, 4 plays or something like that. So the impact of your action is not necessarily immediate. And so you need to see if your problem fits this paradigm. Like, do you have sequential decision to take to solve your problem? The second challenge is having a measurable outcome. Basically, can I say at some point that I finished my task, like the assigned task, and how, and preferably to assess how good I achieve it. So if you don't have a metric, you it will be complicated to apply error. So if the the task at hand is a bit qualitative, you can't really say if easily if your agent is doing good or bad. That can be prevent you from applying reinforcement learning. And once you answer these two questions, maybe the hardest part is how to frame your problem as an MDP, or Markov decision process. So what's a Markov decision process? So it's classic formulation for sequential decision-making systems. So, and where an action just does not just influence its immediate reward, but have like a consequence on all the future states that would happen after it, and by consequence the future reward. But the decision you take will depend only from the state where you are. So all what happened in the past doesn't really matter. If we look, for example, in this graph, if we are in the wake up state, it doesn't matter what if we were before at watching Netflix or taking a nap or whatever, or like the decision, like the outcome of the decision we will take will only depend on that state. So, and usually most of the sequential problem, even though if you have this dependency to the past, there are some tricks where you can transform the problem to a Markovian problem. Either you change the representation of the state, or so there are always techniques to get back on your feet to a Markovian state. So once you identified all this, how do you drive your project? So for the moment, maybe this is the most mature way that you will find in the literature to tackle this kind of problems. So it's inspired by the CRISPR-DM life cycle. And basically, you will start with the problem definition, define your environment, you refine your MDP, your Markovian decision process. Once you are good with your formulation, you start modeling, implementing. Probably you'll find flaws in your modeling. You can simplify stuff. You go back to the second stage where you refine that. And once the model, the implementation are mature enough, you go to evaluation and deployment. So what to check if you are tackling reinforcement learning problem. So as we explained a bit earlier, you have to frame your problem as a sequential process. You have to define what's the agent, what's the environment. It may sound easy, but in real and practical application, it may be a bit difficult. sometimes it's not that obvious to trace a line between the agent and the environment. So one of the big questions you have to ask yourself, can I simulate my environment once you have chosen what is your environment? So if I can simulate it, I can accelerate the learning. Then you have to ask yourself, what's the definition of a typical state? And usually the state is not that easy to find. Basically, for example, what kind of feature you will inject in the model can be a hard problem to find, especially in industrial application. It's not easy to see from the current business process you observe what makes a human take that decision. Probably like it's based on some intuition, but this intuition comes from data and so on. So finding what is the specific feature that will make you make the agent take the right decision can be cumbersome sometimes. Then you have to decide what are the actions that I can leverage on the entity. So basically, how do I act on the environment? It sounds easy, but sometimes you have some kind of action that you don't think about, like the action of doing nothing, for example. It can change a lot, your problem. Or can I go back in the past if I have a problem to solve and my agent can take action? Can he undo some action basically? In chess, can he move a piece and then decide, no, I don't want to do it again? In some situation, this can help you or make things complicated depending on the problem. And last but not least, what's your success and failure criteria, which will help you decide of your reward. And in a lot of cases, the success or failure criteria is different from the reinforcement learning reward, because in the reward, you will try to sometimes hack it a bit to avoid some situation where you want to avoid your agent to do stupid actions while trying to achieve the goal. So you, for example, you penalize him for doing some kind of actions, while at the end, like the success criteria is a bit different. So sometimes this problem can be quite challenging, where how to make your reward, your reinforcement learning reward, meet the business criteria. Ideally, it should be the same, but it's not usually possible. So, based on my own experience and my team, maybe some tips if you're starting a reinforcement learning project. First thing is try to simplify your problem to the bare minimum. Like try to see in your problem what's the most important task you want to learn, or what we call skill. And try to create a toy environment that help you simulate that skill and learn that skill, and then add complexity gradually. Don't try to solve the big problem from day one. And then you have supervised learning models. Uh, Supervised learning models will help you to iterate through your model more quickly and start the reinforcement learning loop more easily. Basically, collect data from your simulator, but don't do the reinforcement learning. Just do supervised learning. Once your model is mature enough, you plug it in RL. Of course, it's easier to say than to do, but this is for us. It helped us in a lot of situation. Then invest in a heuristic, like a method baseline that uses classic programming algorithmic to solve your problem. If you have that, you can use it as a teacher for your agent. And then don't reinvent the wheel, especially if you're not doing research. Try to rely on mature reinforcement learning algorithm and don't try to re-implement one by yourself. They have a lot of frameworks. So here are some applications where reinforcement learning is applied in real life. Uh, for example, this one is from Covariant AI, a company based in California, and they are the first probably to deploy a real robot that learned to do some industrial task in real life. And this kind of robot is deployed in Germany, for example, right now in the automotive sector. Basically, the operator doesn't have to program the robot; they just show it the task, and the robot will do it. This one is the Atari agent I talked about a bit earlier. And this one, maybe some of you have watched what OpenAI did with Dota 2, and where they trained an agent to play OpenAI 5 by 5, so against 5 world players, and they beat them. And there's a documentary that just been released around how they did it recently. Another example is from Electronic Arts, where they basically train uh, an agent to drive in a video game. And you see it drives like a human. So applications are quite wide. You can apply it in resource scheduling, in robotics, software testing, drug design. I'm showing this toy problem we're working on, where basically we trained an agent to solve a maze, a random maze. So the agent never seen these mazes, but it's able to find its targets instantly on any kind of mazes. So like a maze self-driving car. It can be used in recommender system, for example. And finally, if you want to start reinforcement learning, you don't have to reinvent the wheel. There's a lot of frameworks. There is ArrayLib, which is probably the most mature, but also sometimes a bit complicated. If you are doing research, maybe the best thing is to do Acme. It's a framework developed by DeepMind. There's Intel RL Coach, which is quite good. Of course, the frameworks of deep learning, TensorFlow, and PyTorch. There's also something called TF Agent, but it's still not super mature. It can help prototyping quite quickly. And maybe the most important one is OpenAI Gym, which is a kind of interface that unifies the way you define the interface of an environment. So if you have an environment and you plug it to OpenAI Gym, you can directly use it with Ray, with ArrayLib, Acme, etc. And if you want to learn about reinforcement learning, I would advise you these two, like the engineering side, not the research. I would advise you to read these two books. The first one is Reinforcement Learning for Industrial Application. It's quite recent. I think it was released in March 2021. And it's super good, explaining the engineering side of reinforcement learning, and it comes with GitHub examples and so on. And the other one is Deep Reinforcement Learning Hands-on, which is super good one. I think for me the first book that was written around reinforcement learning engineering, and If you have time, maybe for online courses, I would recommend deep reinforcement learning course, nano degree in Udacity. It's a bit expensive, but I think it's worth the investment if you want to do it. So thank you for your attention, and if there's any question.
Thank you, Amin. It was a really interesting talk on reinforcement learning. Um, if you'd allow us, it would be nice to read some questions that we've got from the streaming platforms, from YouTube and Twitch.
Yeah, yeah.
So the first question from a student perspective is saying that, is it better to start learning machine learning first, then jump into reinforcement learning, or can I learn reinforcement learning directly? Also, is there any other technical requirements before starting to learn reinforcement learning?
Definitely, learning RL is harder than learning deep learning and machine learning. And doing deep RL, as it's in the name, deep, you have to understand machine learning because part of it, it's machine learning. But you also need good skills in software. Like the complexity of RL makes it more difficult. Like you need the math background, but you also need the computer science background. So you have to kind of invest in both in parallel. While in deep learning, machine learning, I would say the barrier in terms of software knowledge is a bit lower.
Mhm. Yeah. Also, and how hard is it to apply reinforcement learning for real world problems, like in enterprise level problems? I mean, given your experience in with InstaDeep and
Uh,
everything.
so
So after just
I didn't
video
hear
games,
clearly Mm. Yeah.
um,
So
the,
video games, yeah, video games may seem easy, but sometimes it's harder than real life problems. But I agree that it's quite difficult these days to apply RL on real problems. Like most of what you see is research. There are few companies in the world trying to solve real life problems with RL. InstaDeep is one of them. Um, uh, I've shown an example of covariant AI. For a long time, no one thought like RL will end up in a factory for cars, but they've shown it's possible.
yeah,
Uh, I think one of the problem is the difficulty of the engineering. It's not just because like probably we have some of the tools right now to do RL in real life, but it's so hard to get all the pieces together, and most innovations are quite new. So we are still in the early days. I expect like RL will be more widely used in 3 and 4 years.
yeah. Speaking of InstaDeep, you just mentioned InstaDeep and their efforts to apply reinforcement learning in real world problems.
Any other
So
question?
this question also is curious whether are any cool projects that you worked on at InstaDeep that where you found reinforcement learning particularly useful that you would want to share with our communities today.
Yeah, so we're working on using reinforcement learning, for example, for routing printed circuit boards, basically design like electronic boards using reinforcement learning.
Mhm.
It's super hard problem. Like people trying to automate this for the last 40 years. We still have using most of it. We are applying it, for example, for scheduling trains, like at the level of a big country. We're applying it for logistics, for for biology. So the applications are quite wide.
Uh,
I agree
okay,
that
but
it's quite hard to apply in real life.
yeah. Well, brilliant, because there's few companies who actually overcome all the problems, and there's actually fewer initiatives on to implement solid standards for the LL community in general to become able to iterate faster in building robust LL systems. Um, Actually, another question also is wondering. You see, in the illustration that you showed us from Andrew Karpathy, I suppose, uh, he
Yeah,
said, will software 2.0 also involve what we know as MLOps?
yeah. MLOps, like if you let me go back.
Because this is the missing component in the reinforcement learning pipeline. You see, the machine learning community has grown up in the last decade to have what we call as MLOps, but in RL, I believe it's still young to have
Yeah,
something
like
equivalent.
MLOps, like you still have MLOps in RL, but it's super hard. I think the level of the Devops you need around an ML, a reinforcement learning project is way more like sophisticated than what you do in ML. For example, I'll just give you the data agent that was trained by OpenAI. Basically, the model is training continuously for like 9 months with different versions, uh, and they were using like I think 200 GPUs at the same time, all the time, during 9 months. So you can imagine the difficulty of running such systems. So of course, in machine learning, ML ops is a big part of it, but a lot of companies like built off-the-shelf tools for that. In RL, we're still in the early age, so you still have to do everything by yourself. Uh,
Mhm.
Also because you don't have the base of users that justify like something off the shelf yet, I think.
Yeah. Well, I believe this is a problem, but I hope maybe in the coming few years, the ecosystem will grow enough to overcome these problems from
Yeah,
theoretical and practical
for
aspects.
sure. Like, as I
Um,
said, it's the at the heart of the reinforcement learning problems. And example, I think there's like Greg Brockman, who is now the CEO of or CTO of OpenAI, has a kind of podcast where he explains how they did the first version of the Dota 2 agent when it was just 1v1, one player against the computer. And he says like the research part and things like that is just one guy, like 10, probably 10 or 5% of the team. All the others are people skilled in software and DevOps and this kind of things, how to distribute things. Um, so yeah,
yeah,
like the
yeah,
pure
brilliant.
modeling side is just a small part of it.
Yeah. Well, I'm curious to see what the future will hold for us. For now, I think our time is up with the reinforcement learning. It was really great hearing all this from you, and it was so kind from you to answer all these questions. So thank you for the precious insights that you provided us with. I'm confident it will inspire different members of our community as students or even as coming of age entrepreneurs to either start learning about RL or to consider solving their enterprise problems with RL. Now, before we wrap up, would you want to leave any final words to our audience or to the GDG community in general?
Yeah, thank you for the invitation. It was a pleasure for me to talk here. I hope after the pandemic, maybe we organize real life events and have the
I really
opportunity
hope
to
so.
visit Alger. So my I'm like I went only once to Alger for like didn't even stay more than a day there. So, but
Yeah, you
maybe
gotta come back after the pandemic. I mean, it was really nice having you online, so I can only imagine if it would be in real life. So I hope we'll see you again in the future, in the near future, I hope, to tell us more about the cool stuff InstaDeep will be cooking for us using Era, because I'm sure it won't stop.
thank you.
Yeah.
See you soon.
Bye bye, Amy.
Thank you. Bye.
Thank you also to our audience for being so numerous in this first talk. Now we're gonna have a short break and then meet again for a couple more interesting talks on AI. So see you in 3 minutes, I guess, or 4 minutes. Hello, welcome everyone back again to our second day of Devfest 2021. Also in our second session of the talk series. In this session, we will be joined with our dear speaker Hadjer Benmeziane. She is a PhD candidate on AutoML, and she is also the founder of School of AI Algiers. So welcome, bro, Hajar. It's really nice to have you among us today.
Hello, I'm really honored to be here, and thanks for the invitation.
You're welcome. You have your talk duration, which will be 45 minutes max, and you're free to start whenever you're ready.
I will share the screen. Give me a second.
Okay. Take your time.
Okay, can you just get up the slides? I cannot. Okay, perfect.
Yeah. Good luck.
Okay, thank you. So I can start?
Yeah, sure.
Okay. So hello everyone. I'm Hadjer Benmeziane. As Akram said, I'm a PhD student. I'm working on AutoML in Université Polytechnique de Hauts-de-France. And I'm really glad to present this AutoML, which is kind of revolutionary paradigm in machine learning, but we're going to discover it more in this talk. So basically, I outlined this presentation into two stages. In the first part, we're discussing like theoretical concepts of AutoML. What are the components? How can we use it? What are the advantages? And what are the challenges of AutoML? And in the second part, we're gonna work with an imaginary company, and we're gonna try to implement or help this company create its own machine learning pipeline without needing a huge data science team. So as a machine learning engineer, how can you use like the AutoML tools to improve the company machine learning pipeline? So this is the two stages of this presentation. So whenever we finish the first stage, if you have any question, we're going to stop. You can ask any question you like, and then the second stage. And the second stage will be more like, here is the data of this imaginary company, and here are the tools, and this is what we can do with the tools and this data. So basically, I will start with some machine learning basics, just so as we can understand the rest of the concepts of AutoML. So being data-driven now is required to lead any industry. And by data-driven, we mean that every decision is based on a set of data that we stored somewhere. So machine learning and deep learning are, of course, the basic blocks of using this data and extracting some insight from these data. And these are like the pivotal algorithms in artificial intelligence. So they are used in many applications, robotics, autonomous driving, like the smart keyboards that we have in our smartphone, and etc., etc. So, and of course, I couldn't not make this graph that we can find everywhere, just so as we can have our concept set straight. Like the artificial intelligence is the fields that makes a computer decide or make decisions. And then inside the artificial intelligence, there is a field that is called machine learning. And it groups all the algorithms that are data-based, so that learns from the data. So this is machine learning. And inside machine learning, there is a concept that is deep learning, where the algorithm that learns from the data are neural networks, are deep neural networks. Okay. So basically, what is the difference between a machine learning algorithm and previously used algorithms? So if we want to create a classifier like cats, dogs, and snakes images classifier, so we have like images of dogs, images of cats, and images of snakes, and we want, given an image, we can classify it, either it is a cat or a dog or a snake. So if we want to do it by explicit conditions, we need to write down all the differences between the images of cats and dogs and snakes. So for example, like here we have like a snippet of a code where we wrote if the image contains no legs, so it is a snake. Else, we need to look for more features or more differences to differentiate cats and dogs. Now, in the ML-based algorithms, it is slightly different. We're trying to do it like intuitively as we human learns. So basically, we have a function, a mathematical function that predicts the probability of an image being a cat or a dog or snake. And we use this, this in a randomly initialized function. We use it to classify a bunch of images. So we give it like 100 of images between cats and dogs and snake images, and then we use it to try and classify these images. And based on its results, we can calculate a certain error. So for example, if we give it an image of a dog, and this function outputs the highest probability for the class cat for this image, we know that this is an error. So we can calculate how many errors this function is computing. And we can adjust its weights, or this function, we can adjust it in order for another run. When given the same image of dog, it will output the correct label, which is dog, or the correct class, which is dog. This is why we repeat this process, because we're adjusting the weights, or we're adjusting the function in order to get a more accurate result in the future runs. Now, when we say weights to adjust, it's a little bit weird because we're not really seeing this function, and we're not really adjusting the weight. So you need to have an example of some sort of machine learning algorithm. And the easiest, I think, the easiest machine learning algorithm to display is the neural network. So here we have a neural network with 3 layers. And in each layer, we have some sort of nodes. So the round circles here are the nodes, and they are connected with edges. And the nodes can be either a value, can hold a value, or hold the value of an input value, or hold the value of a computational value, a computation results. So for example, the first nodes here are the pixels values of an image. So this is the first pixel, the second, the third, etc. And then in here, in the second layer, the first node will hold the value of this pixel value, the first pixel value multiplied by the weights, or the value given by the edge. So when we say we need to adjust the algorithm, we need to adjust or to modify the weights of the edges, in order for the probability, or the third layer, the results in the third layer will be closer to the accurate results. So this is when we say adjusting a machine learning algorithm, this is what it means. And this is what training means, actually. So training an algorithm is trying to adjust these weights in order for the results to be accurate or closer enough to the output we want. Okay. So now if we want to see the whole machine learning pipeline from data collection or data acquisition to the deployment of any machine learning model. So here it is in this figure. So first we collect some data, or if we are a company that has already some data stored, we go directly to the second phase. And the second step is to clean this data. So probably we'll have like some empty values or some weird values inside. So we need to clean it, and we need to prepare it. Preparing it means that we know which model we're going to use, or which algorithm we're going to use. So we need to put it in the right format. We need to put each data in the right format. So this is data preparation. And then we have feature engineering. So in deep learning, we know that feature engineering and model selection are intertwined. So we have one model that does the feature engineering and the classification. But in general machine learning model algorithms, or classical machine learning like decision trees or any other algorithm, we need to separate the feature engineering from the model selection. So basically, feature engineering is trying to either construct some new features, or just assess the importance of each feature. So we have like 10 columns, 10 features, which one of the features will help me classify my data, has a certain correlation with my targets, etc. And if I have like 100 or 1,000 of features, can I reduce this number of features in order for my model to work well? And the fifth phase is to select a model. So either a decision tree, a neural network, a deep neural network. Even in deep neural networks, we have different models, like a convolutional neural network, a recurrent neural network, etc. So in this phase, we have like a different set of models, but each set of model works well with a set of data. So for example, with images, we can have either convolutional neural networks or vision transformers. But with text, we see that transformers are better at dealing with text and sequential data, but we can have like a certain inductive insights that we can have from the standard model that we can find in the literature. And once we decided which model to use, we go to the training. And in the training, we know that we need to have to set some hyperparameters like the learning rate, etc. So we need to set these hyperparameters in order for the training to work. And then we have this phase where we call the tuning, the hyperparameter tuning. We know that when we select a model, so in this phase, probably we will detect that we messed up in some sort of step, either with the data cleaning, with the data preparation, with the model selection, or with the hyperparameters that we defined in the training. So we can see that either our model is really overfitting or underfitting, or probably our model is not learning at all. So we need to adjust the hyperparameters we did in the previous steps. Or even not the hyperparameters, but even like the cleaning, we messed up with the cleaning, or we messed up with the data preparation. So in this phase, we get back to other steps and correct them or try different hyperparameters in order for our model to give like some more accurate results. And this phase is like just behind it, like the validation step, where we test our model with new data and see if this model is working well, is generalizing well, etc. And in this phase, we can say, okay, I'm fine with this model. I like it. It is good. So I'm going to deploy it. And the deployment is like some sort of is the phase. It's like another complete pipeline where you can have it, where you can compress the model. You can try to deploy it in some smartphone, but it is too big. So you try to use different techniques to shrink the model so that you can deploy it. So this is basically the traditional machine learning workflow. So I want to discuss this hyperparameter concepts in order for you to understand what are the hyperparameters. So the easiest way to understand what's a hyperparameter and what's an architecture is through an example. And I think the easiest example is a convolutional neural network. So basically, when deciding which model we're going to use in deep learning, even if we decided, okay, I'm going to go with convolutional neural network, I have to decide different parameters or different attributes of this architecture, of this convolutional neural network. So here I display like a standard convolutional neural architecture. We start with the input. The input is an image. And then we go through a series of convolution downsampling, Now, and finally, we go to the fully connected neural network, the final classifier that will output the probabilities that given an image, it is a dog, or given an image, it is a cat or a snake. Now, to see how hard it is for a machine learning engineer to design an architecture, you can see here the different attributes or the different hyperparameters that a machine learning engineer needs to define. So the first thing it needs to define is the type of operation per layer. It's the blue, the blue writing here. So in each operation, the machine learning engineer needs to define whether it is a convolution or a pooling or even any other variants of the convolution, like the depth-wise convolution, the dilated convolution, the grouped convolution, etc. So in each layer, the machine learning engineer needs first to define which operation per layer. Once he is done with that, so we have the complete architecture. We're not done yet. We don't actually have the complete architecture. We need to define some hyperparameter, which are called the architecture hyperparameters. The examples of that are the number of convolutional layers, the number of units in the fully connected layer, or even the hyperparameter of each operation. Like the convolution has the kernel size, the stride, the padding. So these are all architecture hyperparameters that are that needs to be defined before training the architecture. So as a first step, the machine learning engineer needs to define an architecture. And defining the architecture means defining the operation per layer and defining the architecture hyperparameters. So the hyperparameter of each operation and the number of layers, the number of units per layer, etc. And then the second type of hyperparameter is the training hyperparameters. So these are hyperparameters or parameters that depends on the type of training we want to do. So depending on the architecture we have, depending on the data, we have a certain we have a certain learning rate optimizer that we can use. Like ADAM is more generally used for text data, and AdaGrad is generally used for image data, but it can change depending on the data set we have. So we need to define the learning rate, the momentum, the batch size, etc. Okay. So this is just to see that really the work of a machine learning engineer requires a lot of experience with different data sets and different architectures. So this is the problem AutoML is. This is one of the problems AutoML is trying to solve. Okay, so now machine learning 2.0. Now that we know the basics of machine learning, we know what is an architecture, what is the pipeline of to create a machine learning architecture model. So now what is machine learning 2.0 and how AutoML can help us create this machine learning 2.0. So basically, the new AutoML workflow will be like this. Data acquisition, which we obviously need to collect some data. And after that, all of the steps that are after the data acquisition, data cleaning, data preparation, feature engineering, model selection, model training, and tuning and validation are automated. What does it mean automated? It means that we have a certain search. We're going to search for the best model, the best hyperparameters, the best way of cleaning the data, and the best features in our data, in order to do it directly in one pass, rather than trying different things from a machine learning expert. So basically, AutoML can allow non-machine learning experts to build and use machine learning systems for handling targeted tasks without the need of domain knowledge. So we just need to insert the data. We obviously need to know which task we want to solve and what type of data we have. Either it is an image or a tabular data or text data or even a forecasting. So it is one column, one feature, but it is over time. And we also need to know what is the task we want to solve. Is it image classification? Is it regression? Is it a text classification, etc.? So we just need to give it two different values: the type of data, the data itself, and of course the task we want to solve. And the AutoML tool will directly process different types of architecture, different types of cleaning, try to figure out which are the features that are the most important in order to and the output of this AutoML tool is a machine learning model that is already trained on the data and is ready for deployment. Okay, so the benefits of AutoML are a lot. The first one is to allow non-experts to build machine learning systems. But to be honest, we are not quite there yet. We are not allowing non-experts to build machine learning systems directly. So AutoML is not like, okay, we don't need data scientists, we just need an AutoML tool. Not at all. We still need some machine learning engineers and machine learning experts to run these tools. And it's mostly, most of the tools now are helping machine learning experts to improve their models and to make them better. So the four benefits that are after this, the first one, are mostly for all machine learning experts. So the second one is to reduce the cost of hyperparameters tuning. So rather than spending weeks and weeks trying different values for the hyperparameters for the learning rate, going from 0.003 to 0.001, etc. So trying them all, we reduce the cost of this hyperparameter tuning by efficiently searching in the space of the values of these hyperparameters. Now, the third benefit is to allow machine learning practitioners to improve their model's accuracy, of course. So by allowing them to use hyperparameter tuning efficiently, we can improve the model's accuracy from 2% to 5% with only classical models, machine learning models. So if you can see here in this graph in the right, so this graph is from a paper, Data-Driven Advice for Applying Machine Learning to Bioinformatic Problems. So basically, they tried the classical machine learning algorithms like decision trees, and they tried the default hyperparameter values provided by scikit-learn, and they compared this model, the obtained model, with another model that is after fine-tuning the hyperparameters. And they've seen that there is a difference of 5% approximately in the accuracy of the two models. So this is really important because this is also used in like deep learning competitions where they say that cross-validation or tenfold cross-validation is the most important steps in their solution. Okay, now the fourth benefit is to allow machine learning experts to find new architectures or new models like MobileNet version 3. MobileNet version 3 was developed by Neural Architecture Search, and Neural Architecture Search is one component of AutoML that we're going to discuss in later in this presentation. And the fifth benefit is to allow machine learning experts to find efficient architectures for different hardware platforms. So this is really important. If we have like we want to do object detection on a car, we want the car to detect the person and to stop really at the right moment, not before, not after, but at the right moment. And to do that, we need efficient models that are run on the car, on the autonomous driving car. And to do that, we need architectures that are fast and efficient and hardware efficient. So using AutoML tools, we can decide what we're looking for an architecture that is good in terms of accuracy, but also but also fast, and maybe even like in terms of memory size, we can shrink we can find the smallest architecture with the highest accuracy. Okay, so this was for the AutoML benefits. Another idea I want to say here is the no free lunch theorem. So the no free lunch theorem says that we cannot have one architecture, one model that is the best for all different data sets. So this is important to know because each data set will have its own architecture and its own model. So when using like standard models, we pick a standard model that is trained on ImageNet, for example, or CIFAR10, and we use it on our own image data sets. We have to know that we need to tweak a little bit the architecture or completely retrain the architecture sometimes to really find the best model for our data set. So we need to know this in order. This is why like AutoML tools are really efficient, because given a data set, they are going to give us the best architecture. Okay, now the AutoML components are, I divided the AutoML components into three categories. The first one are the automatic data processing. So all the tools that are dealing with the data cleaning, the data preparation, the feature engineering. So all of these tools are categorized here. The second is hyperparameter optimization and neural architecture search. So sometimes neural architecture search, in the literature, you can find it like a subcategory of hyperparameter optimization. But I think it's important to distinguish the two, because neural architecture search tries to find the best architecture. So basically, they are trying here Yes. So with neural architecture search, we're dealing with these two components. So we are trying to build the architecture. We are trying to find the operation per layer and the architecture hyperparameters. So all the blue and red writing. And with the hyperparameter optimization, we're mainly focusing on training hyperparameters. So we're trying to find the best learning rate, the best momentum, the best batch size, the best optimizer to train our architecture. So this is how we can distinguish between hyperparameter optimization and neural architecture search. And all of these tools have these components in them. So they have, the first component is the search space. So you can see like the graph on the left. The first component is the search space. The search space is the set of hyperparameters or architecture operations that we are trying to build with. So it's like a Lego box where each Lego is either a hyperparameter with different values and or an operation. And basically, the search algorithm will try to combine this to build one architecture. And to find the best architecture, it needs to evaluate the architecture that are built in order to see, okay, now I've done like, I mixed this Lego with this Lego with this Lego. Okay, let's see what is the performance of this architecture. And we need to evaluate the accuracy of this architecture, like training it on our data sets. And then we know that this combination is given 50%. So we need to either remove one Lego or add some more components to the builds, to the architecture, in order to find the best architecture. And doing this like gives us basically the main drawback of AutoML tools, which is the time-consuming search. So basically, we know that training an architecture is extremely expensive. If we want to train an architecture on ImageNet, it takes like 2 to 3 hours. And if we do that for each block that we are going to compose, or each architecture that we're going to compose, this will take a lot of time. So this is one of the challenges of AutoML that is taking a lot of time to compute. Another disadvantage of AutoML or challenge of AutoML is the huge search space. So if we define our search space, we can define it by the number of operations and the number of hyperparameter values, and we can even like let's give a simple example. So for the learning rate, I can define my search space with different values for the learning rate. We can say, okay, I want to try 0.01 and 0.1. So this is a really small search space, but I can make it really big. I want to try 0.01, 0.02. I want to try from 001 to 1 with a pace of 001. So this is like with a step of 001. So this is really a huge search space, and we need to evaluate a lot of architectures. So if we do that, it requires a smarter optimization methods. And by smarter optimization methods, we mean that the way we're gonna explore this search space is through different strategies, like using random search rather than grid search, or using evolutionary algorithm, or even reinforcement learning, as the previous talk explained. So we can also use reinforcement learning here to explore our search space more efficiently. And also we also have another challenge, which is each data set its own correlations. So this is what I talked about ImageNet. When we have like a standard model that is trained on ImageNet and we want to use it on our own data set, we need to know if our own data set is somehow correlated to ImageNet so that we can use the same model, or we need to search for a completely different model. Now, the fourth challenge is the bias in the search space. So as you may get from this figure, in the search space, we're trying to define our operations and our hyperparameter values. And these hyperparameter values, or these operations, are extracted from standard models. So we can have like, As here, we can have a convolution, a pooling, a depth-wise convolution, a dilated convolution, a grouped convolution, and all of these operations are extracted from previously known architectures or standard architectures. So this is kind of a human bias into the search space. Like, should we integrate this human prior knowledge into the AutoML tool, or should we try to make something mathematical or completely new so that the AutoML tool will completely give us a new architecture? This is what AutoML 0 of Google are doing, where they are trying from completely zero with only the mathematical operations and trying to compose a new architecture. And they found that their reinforcement learning agent is now creating like some operations that we already use, like the normalization or the logistic regression, etc. So I think this is the end of the first phase. I don't know if you have any questions. Okay, I'm gonna just check if there is any questions. Okay.
Hey, Hadjer,
Hey.
I'm back. Sorry, I left you
No
hide.
problem.
Yeah, so there is actually plenty of questions.
Okay,
The first
perfect.
question going in the screen. Iman Hamzawi says she's wondering whether correcting the model by the AutoML method, by the AutoML tool, would put us in a risk of overfitting, or does the performance englobe the overfitting case too?
Okay, so in the AutoML tool, we also take care of the overfitting. So if we detect overfitting, we try to remove it, or we try to train another model that overcome the overfitting. So we can also add some regularizers in the training or in the building block of our architecture if we detect some overfitting.
Mm-hmm. Okay, also, the gentleman is wondering, in terms of budget, is it more efficient to use an AutoML tool, or is it easier to hire a data science or machine learning dedicated team? So is it cheap enough for local companies or startups to use it?
Okay, so I think this question will be answered by the second phase, but for now, let's say that I didn't say that you don't need to have a DS team or an ML team in your company. It is always required, and these are the ones that are going to use the AutoML tools actually. So for now, we are not yet in the space of, okay, I have a tool and I just give it the data and it will output a model magically. So we're not yet there. We still need one or two machine learning engineers. But I think, in the future, of course, if the company has a lot of data and knows that it can benefit from the data, it needs a machine learning team. But if it has like some small data and it wants just to be like some sort of data driven, but not that much, it can like just use the AutoML tools and hire just one machine learning engineer.
Mm-hmm. So if we have some other questions for the debate, the only question that I see relevant before passing to the second phase. Okay. Here Zakaria is asking about is there any drawbacks or limitations before considering using AutoML for approaching a machine learning project? Or will that come afterwards?
Okay, so I'm trying to think of any of the drawbacks that are not mentioned in the challenges of AutoML. So it depends on what kind of machine learning projects. So if we are in a research project, we don't usually use AutoML unless we're working with AutoML. unless we're working on AutoML. So if we're in a research machine learning project, we don't consider using AutoML, but we use like really machine learning insights, machine learning engineers with insights that can help create the best, the more accurate model. Now, considering using AutoML in competitions like the cross-validation and trying to make, rather than using a grid search, just using a random search or a more smarter optimization method, this is really interesting because it will help, like in a few amounts of time, getting a really good results.
Okay. And another question that I found relevant to this one is whether the search algorithm or how it operates. Maybe if you could give us a glimpse on how the search algorithm operates. So here, I believe they are curious whether if the algorithm is learning based, so would this be logical to call AutoML as a type of meta learning, aka learning how to learn or what to learn?
Yeah, exactly. So AutoML can be both actually, and we use meta learning in AutoML. So you can see like AutoML is all of the techniques that are trying to automate creating a machine learning model. And then we can use meta learning inside AutoML to adjust the optimization methods and to help them. Like, for example, we can use, so rather than training each architecture when searching for the best one, rather than training them to evaluate, we can use a hypernetwork. And the hypernetwork is one type of meta learning which predicts the accuracy or predict the weight of the architecture rather than training it. So if we take an architecture in the search, we take an architecture, we use the hypernetwork will provide the weights of the architecture, and we automatically get the evaluation or the accuracy, rather than training and spending hours of training on each architecture. So meta learning is really an important, has a really important place in AutoML.
Brilliant. That would also be really promising for the problem of maybe that you mentioned, which is the bias in search space.
Yes.
So when we are doing meta learning, we are given the agents or this tool in general an opportunity to learn for itself or to know what is good instead of telling it by human prior knowledge. Don't you think?
Exactly.
Yeah,
it has a really important aspect.
Yeah. So there are other questions like asking you about reward projects that you used AutoML and everything, but I thought maybe I should ask you first, would you rather answer them now or leave them to after the second phase?
Yeah, I think we can leave them after the second stage. Okay.
All right. Okay.
Okay, so we are getting back to the presentation. All right. So now let's get back to the second phase of this presentation. We have an imaginary company. And this imaginary company, like I thought of the simplest type of data that a company may have, and they want to be data-driven somehow, and they want to have like a small machine learning pipeline in their system, without really needing machine learning for any other like any other product. They just needed to run the company, but not to use it in any other product. So, okay. Let's say we have an imaginary company, and this imaginary company wants to predict the attrition of its employees. Basically, the attrition is if they are going or not, they are going from the company or not. So we have these data where we can have like the age of the employee, the business travel, that is, are they like traveling rarely, frequently, or and the daily rate, the department, the distance from home, the education field, and many other features. So basically we have 35 columns. -1, which is 34 features, and we have this attrition attribute, yes, no, if the employee is going or not. And basically these data are from the IBM Human Resources Analytics. and they are available in Kaggle. Okay, so if we have this data, how can we create a model without really seeing the data, or like even not touching the data, just a dot had with panda, just viewing the whole data and then putting them into some sort of function, and that's it. So how can we do that? The first thing they can do is to use commercial tools. So using commercial tools like Google Vertex AI or AWS AutoML, they have to create a certain project, and in the project, as you can see here on the left, they have to decide if their data is tabular, images, text, or video, and they have to choose which task they are going to use. And basically, after a few filling the forms, they have like their machine learning model completed and ready for deployment. And even like in Google Cloud platforms, you can have it already deployed and you could just call it directly. So yeah, this is for the commercial tools, but of course, these are paid tools. But let's say we have like a pretty good amount of CS engineers, and we want to make them and machine learning engineers, and we want to have them build our own machine learning pipeline. But they don't have like a real machine learning background. They cannot build a real complete model from scratch. They just need some sort of tool, like a framework that can help them create their machine learning their machine learning model. So here we have like different tools, open source tools like AutoScikit-learn, AutoPytorch, and AutoKeras. And basically these tools deal with the data cleaning, the feature engineering, and the model selection and training. And tuning. So in using AutoPytorch, of course, I think most of AZ students that knows me knows that I'm Team PyTorch. So I'm gonna use AutoPytorch here, like to display this example. So basically, using AutoPytorch, they can call this tabular classification task. And using this tabular classification task, this is what we're doing with like a commercial tool with Google Vertex AI. We need to choose which type of data we have and which task. So basically, this is tabular, and we're doing the classification task. So we import this object, and using this object, we create this API. So the main parameter of this API or attribute of this object is the seed. The other ones are just directories to put sorry to put the temporary files and the logs of the search in order to rerun the search if we want. And then we just call like api.search, and we give it all the train and test if we divided our training and test data. If we didn't divide, we can directly like give data equals data. And we give it all this. We obviously give it the optimizing metric. As you can see here, we can give it the accuracy. We want to optimize the accuracy of our classification. We can also give it other metric that we computed, like we create a function that that calculates the FPS, the frame per second for an object detection, an object detection model, and give it as an optimized metric here. And we can also have, we can give it like the total wall time limit and the function eval time limit. So basically these two parameters, these two arguments, the first one, the total wall time limit, it means how many, the duration of the total search. So after an amount of time, we want to stop. If the search doesn't converge, and most of the time it doesn't, we want to stop after a certain amount of time. And also we give it a function eval time limit, which gives like this, sorry, the limit of time per second for the evaluation function. And if we do that, at the end, the API is basically a model that will output the predictions given a Y test or a X test. So this is how AutoML's tools are working. And I think I'm done with the presentation. If you have any questions, I want to hear them.
Thank you, Hadjer. It was really nice presentation, especially the second phase. I really liked the. I mean, that's really the part that I didn't know of before from AutoML. So if we proceed to the questions like before, okay. So this one we've seen it already. Maybe the one that came to my mind right now after the second phase is if we opt for open source solutions, for example, for open source AutoML solutions. So the API search, the equivalent of what API.search method would do is to run the search algorithm, right?
Yes.
So here, if I am a company and I have an existing infrastructure, so I can run that on my hardware, on my physical hardware, and that would be the only so it will do the search. So here, if it's a direct search method or just a search method that requires hardware, here the problem would be solved. Then I wouldn't need commercial tools. But if it's a learning-based search tool, won't I need won't it be better to opt for commercial tools like Google's or AWS's, because they would have more experience from other clients, so their model would be better at learning what architecture to put?
Okay. Okay. So not necessarily. Their model won't be better, like necessarily. This is like you can have like with AutoScaler and AutoKeras and AutoPyTorch, they are really doing the same thing as Vertex AI. Sorry, but what you can do is that if I was the imaginary company CTO, I would go with an open source tool, but I will deploy it in a cloud server because it needs like powerful hardware. And if I don't have this powerful hardware, even the search, even the non-learning aspect of the search, like without learning, the search with a huge search space, it takes a lot of time. So we really need like a powerful hardware and powerful parallelization in order to fully complete the search. But yeah, I think that PyTorch are doing a great job at implementing different search algorithms. Sorry. Okay, so they are doing a really good job at implementing different search algorithms, and I think, yeah, I think they are okay. So if we are also knowledgeable about AutoML tools, and like we know which optimization methods are good, which are not good, with AutoPyTorch we can even modify this. So this is really good. Yeah, with commercial tools, you can also we can only apply their tools, but with AutoPyTorch, as it is open source, you can modify the search, you can improve it depending on what you have on data set and architectures.
Yeah. But don't you think that this is actually hard because in order to customize something just for your particular use case, which is dynamic too, so my use case can also change in the time. So maybe when we have one big AutoML tool that learns from a huge audience of users, it would have a good data set to learn how to search more efficiently.
Yeah, so this is why I am suggesting to create the machine learning pipeline for the company. It means that this team will create the perfect AutoML framework for the company. So the commercial tools like Vertex AI won't learn from other companies. They just like standardize everything. But they won't learn from, like, you submitted the data set and you created a model, and I submitted a different data set, but it's similar to yours. It won't take like your architecture to use it on mine. This will never happen. Okay. They will take the same search space and rerun it with our data set.
Don't you think it would be more useful for
Yeah,
AutoML providers to do that?
but it will be like, it will have like some privacy concerns, and so
Yeah,
I don't think they're going to use it directly like this.
I understand the privacy concerns, but maybe if they find ways to detect a correlation between between problem instances, then without using your, for example, we have the problem of cats and no cats.
Yeah, I can give you like an easy answer to that. So you have ImageNet and you have CIFAR10, and it's been like 10 years or more. But finally, we can say that ImageNet images are somehow correlated to CIFAR10 images. So if we can find the best model in CIFAR10, it may be with 90% of chance the best model in ImageNet. But this was like a lot of work, a lot of correlation to calculate, a lot of things to do. And even for now, it's not like a theoretical precise formula that we can use everywhere. So we don't have this. We don't have like, okay, this data set is similar to this data set to use the same architecture.
Yeah. I see.
We're still far from knowing how to compute the correlation between two data sets.
Yeah, but I think it could be really interesting, like a future endeavor, maybe, or for future research to maybe find to add a component in AutoML services where we have a model that's sole job is to estimate your problem instance and to know what kind of other pre-trained solutions could be suitable to just
this is actually one research direction for AutoML, like how to know the correlation between two data sets and how to know if one architecture is the best in this data set, will it be the best in others that are similar?
Yeah. Well, brilliant. That's great. That's just great. If I go back to the audience's questions, I remember one of them who asked you about if you could provide us with any cool real-world projects where you had the chance to use AutoML. If yes, then can you tell us maybe a bit about it, or how was your experience with it overall?
Yeah, so I'm gonna say like two different real world projects. So the first one is not mine; it's MobileNet version 3. So if you can read like the article of MobileNet version 3 and how they can use it for object detection and image classification, you can say that you can notice that how they are using neural architecture search in order to find the best model. I mean, and in order to beat the accuracies of different models and to be state of the art at their time. I think now it's like vision transformers are the best, but at their time they were like state of the art for a few weeks. And for a real world project where I used it is in an AutoML competition. So last week there were like an AutoML competition where they gave us a data set of a company. And this data set was about forecasting. I wanted to use it in this presentation, but I couldn't. It's like a private company data set. So basically, they were trying to forecast rather than classifying the attrition. So is this employee is going or not? They were trying to do it with forecasting. So how many people are going from my company in 10 years? In a month, in 10 months, etc. So, and to do that, we all had to use like AutoML in this competition. And the cool thing about it is that we used like AutoPytorch, and as we were like AutoML researchers, we had to go inside the algorithm and modify the algorithm in order to fit the data and to fit the actual problem. So this is why I wanted to say we are not, with AutoML, we are not removing completely data scientists and machine learning. We need them. We obviously need a lot of machine learning engineers, but it is a good tool to automatically do the fine tuning and to automatically find the best architecture rather than trying ourselves handcrafting different architectures.
Mm-hmm. Well, thank you. I believe even though we didn't recite all the questions, but I believe that you actually mentioned really answers now that I'm going over the questions. So I believe maybe we can call this a talk and just wrap it up, because actually our time is up too. So thank you very much, Hajar, for being so kind to answer all the questions, for the precious insights that you provided, and you always used to provide our UDG community. I'm confident that this particular talk will certainly inspire many members of our community to start learning more about AutoML, or to actually apply them. Yeah. So do you have any final words that you
I think I think I don't have. Sorry for the coughing and the the voice.
All right. It's all right. We just hope you get better soon.
Thank you.
Yeah. So great then. It was nice having you with us today. Hope to see you again soon. Thanks to our audience. More talks will be coming in really soon. So about AI too, with our friends from InstaDeep and others. So stay tuned in our social media pages to find the links for other talks.